Hi everybody, and welcome back to lesson 27 of the Dead Earth game development series. I'm Gary Simmons of the Game Institute, and in this lesson we're going to further develop our FPS controller script. At the end of the last lesson we had the basics in place. We had a controller that could walk, that could run, and could also jump up and down. Strangely, we actually forgot to test the jumping functionality at the end of the last lesson, but thankfully it all works fine. One of the things we can't do at the moment though is crouch, and we're going to need to add that functionality. Now we can't just simulate crouching by moving the camera halfway down our capsule collider, because if we do that the collider won't actually be any smaller. The whole point of a crouch maneuver is that in the game it will allow us to fit through gaps in the geometry that we wouldn't otherwise be able to fit through. So we need to make sure that when we implement the crouch that we also shrink our collider to match so that we are physically smaller in the world and can fit through holes by crouching. And another thing we're going to deal with in this lesson is the fact that at the moment Zombie Jill, when she runs up to us, can pass right through our body. So she's feeding at the moment. Let me just walk right through her to show you what I mean. That will provoke her because she sees me and she runs up to me. Look, she runs right through me. And in fact, because she runs right through me, she ends up on the other side of me, not knowing where I am. So Jill should never be allowed to pass through me, or she'll end up with her back facing us and in an alerted state. And that'll be pretty easy to get away from. Now you might be thinking, well, that's pretty easy to fix. At the moment, our player layer that our character controller's capsule is on is not sensitive or set to collide with Jill's body collider, which is on the AI entity layer. Yes, we could do it that way, but you'll see when I set those layers to collide with each other by going to the edit menu, the project settings menu, and then bringing up the physics manager, and then going down the player layer until I see AI entity and clicking a tick box in there. When we do this, the behavior is not going to be probably what you imagine. Yes, technically Jill will no longer be able to pass through our capsule collider, but what she'll do instead is really confuse our character controller. We're actually stood on Jill's head right now. That's because the character controller is constantly casting a ray or a sphere down at the feet to see if it stood on something. Now the minute that Jill walks into us, the character collider moves us up so that we're stood on top of that surface. So this happens pretty religiously. You know, if you run away from Jill, get her to do it again, she won't bump you out the way, you'll just end up stood on her head. So we're not going to be able to handle it that way. In fact, we're not going to use colliders or collider interactions to handle that at all. So for now, I'm going to disable the player collisions with the AI entity layer, just like we had it at the beginning of this lesson. We're actually going to handle this using nav obstacles, but more on that later on. One of the other things we're going to add in this lesson is, you'll remember when we implemented our feeding state, we had implemented the code that replenished the zombie's satisfaction as it was feeding. But we didn't actually add the code to the parent state machine that would deplete the zombie's satisfaction based on its speed as it navigated around the world. We talked about doing it, but we never actually did it. So we also need to do that as well. We're also going to add a rough flashlight to our player in this level too, just so we can check everything works with Jill as we would expect it to. We'll see how the flashlight is set up, how its trigger needs to be set up, and we'll test that Jill correctly reacts to that stimuli. But the first thing we're going to implement, and probably the most complex thing we will work on in this lesson, is going to be the head bobbing system. In order to implement our head bobbing system, we're going to create a separate class, a little bit like the mouse look class that our FPS controller script is using. A utility class that our FPS controller script can use to generate a nice offset over time that will have the camera bobbing up and down, just like a head bobs up and down when we walk in the real world. I don't know if that's true. I looked at myself in the mirror. My head does not bob up and down when I walk. I'm pretty sure of that. But apparently that's what people expect from first-person shooter mechanics in games. So that's what we're going to do. So let's start by creating our head bob utility class by opening up our FPS controller script. We're going to put that class in that script as well. So at the top of our FPS controller script, we're going to create another class. You can have multiple classes within the same script as long as you only have one that's derived from mono behavior. This isn't going to be a mono behavior derived class. It's not going to be a component It's simply going to be a standard C# utility class that we're going to have an instance of in our FPS controller. So we need it to be serializable so that any settings that we set via our FPS controller's inspector are saved along with the FPS controller component. So we're going to create a new class at the top of our script, just above where we have our FPS controller class, and this is going to be called Curve Controlled Bob. And I'm going to give it the system.serializable attribute. And that's very important. If I don't do that, then when we create an instance of this class in our FPS controller, none of the data will be saved along with the rest of the components data. To understand how our curve controlled bob is going to work, let's call up the image of a sine wave, as I think that really helps describe it. We want the position of our camera to move up and down over time. We want it to move up differently depending on whether it's walking or running also. Our curve controlled bob class is essentially going to manage an animation curve. By default, we'll set the animation curve to have a sine wave, much like you see on the screen now. So in our FPS controller at startup, the first thing we're going to do is we're going to grab the local space position of our camera. What we're after is its height, and we can see in the inspector that's 0.6, so we're going to remember what that is. Each frame we're going to send in to our curve controlled bob class the speed that we're going, and it's going to use that to manage its own internal playhead, the speed at which it is going to step across the horizontal axis of the curve. And when it does this each time, it will also sample the value from the graph, which we can then use as a height offset to either add on or subtract from the current local space position of the camera. The sine wave that you see on screen, if managed in this way, will see our camera bobbing up and down like so as we walk in the shape of the curve. Of course, we're not limited to just using a sine wave. Because it's a Unity animation curve, we're going to get one of those nice little curve controls in our inspector that will allow us to shape the head bob pattern however we like. We also want our head bobbing system to support vertical and horizontal movement of the camera. Therefore, our curve controlled bob class is actually going to manage two playheads, a horizontal and a vertical playhead that can be moved along the time of the curve at different speeds. You're going to see that our curve controlled bob class is going to expose several properties in the inspector that will allow us to configure how the horizontal movement differs from the vertical movement. But they're both going to be sampling from the same shaped graph, however. So let's get straight on with this now. Going back to monodevelop, the first property I'm going to add to our class is going to be of type animation curve. And if I serialize this field, then it's going to give us that nice animation control in the inspector. I've called this bob curve. It's a private variable, but like I said, it's serialized. And you can also see in the constructor for the animation curve, I send in 5 keyframes that define a basic sine wave shape. Of course, we'll be able to change the shape of this completely via the inspector if we want to, but this is what I use in Dead Earth, and so far it works pretty well. With this curve, the horizontal axis is in the 0 to 2 range. The vertical axis is in the -1 to +1 range. Therefore, this animation curve, if used unmodified, will allow us to move our camera through a -1 to +1 offset from its original position, both horizontally and vertically. I mean, that's going to be way more head bob than we need. We don't want our head to be bobbing up and down over a 2-meter range, but that doesn't matter. We're going to create some other variables in this class that are going to allow us to control not only the magnitude of the bob, but also how quickly we move across the curve. Like I said, the horizontal axis of the curve is in the 0 to 2 range, but we're going to move across that differently based on how fast we're going, whether we're walking or running. So let's look at some of the other variables that will help us control not only the values we get back from the curve when we evaluate it, but also that will allow us to keep track of where we currently are along that curve and how slowly or quickly we move along that based on the speed that is passed in. So the first variable that I'm going to create is a private float. It's going to be serializable so we can set it in the inspector, and I call this horizontal multiplier. The horizontal multiplier is basically defining the range that we would like to allow for horizontal head movement. In other words, the head moving left or right. So any value that we extract from this curve, which remember will be in the -1 to +1 range, will then be multiplied by 0.01. The higher we have this value, the more pronounced the horizontal head movement will be. We also want a similar control that will be used to map the value we get from the animation curve into vertical movement for our camera also. So I call this vertical multiplier. As you can see, this is set to 0.02 by default. Generally, we want to see the head bobbing up and down more strongly than we wish to see it bobbing left and right. I find that 0.02 is a good default value, but once again it's an inspector variable, so it will allow us to have complete control over how the value we get back is mapped to vertical movement of our camera in the world. Now, like I said, this class is going to manage two playheads, an X playhead and a Y playhead, that is going to allow us to step through the curve at different speeds for the horizontal movement of the head and the vertical movement of the head. And we're going to kind of configure this, because it's still just sampling from the same curve, by using a horizontal to vertical kind of multiplier. I call this the vertical to horizontal speed ratio, which is currently set to 2.0. In other words, the playhead that we're going to use to step through this graph for Y movement is going to be twice as fast as the playhead updates that we do for horizontal movement. So we're going to see our head bobbing up and down twice as quick. Essentially, it's going to execute that sine wave twice as quickly as we do for the horizontal playhead. So let's create those two playhead variables now that will keep track of the time along the curve. In a moment, we're going to create a function in this class called getVectorOffset. It's going to be called by our FPS controller every frame and pass the current speed that our character controller is going. That speed value will be used to increment the X playhead and the Y playhead. But if we simply added speed onto the playhead, then that wouldn't really mean anything. Our curve is currently 0 on the left hand side and 2 on the right hand side, but what does that really mean? We're just defining a shape. We need another variable that can take that speed and map it into a suitable value that will allow us to step across the animation curve at a decent rate, and a rate that we can control. So I'm going to call this base interval. So this single value will allow us to speed up or slow down the bob. Next up, I'm going to create a private float that I'm going to call curve end time. We're actually going to use this to fetch the time of the last keyframe. Now we know what it is. The time is simply 2, but because we may change the curve in the inspector, we're going to do this via code rather than just hard code it to the shape of this curve, because you may change it. So let's create the first function. It's called initialize, and our FPS controller class is going to need to call this from its start function to make sure that our curve controlled bob class has everything it needs later on. It's going to be passed the bob base interval. This is exactly the same as the base interval. We're just going to copy that value into our base interval private member. Like I said, this is going to be used to control the speed at which we step along the horizontal axis of this animation curve with each update. In other words, it's just our way of controlling how the speed of our controller is mapped to horizontal movement along the graph. So we'll copy the value of that parameter into our private member, and we'll also fetch the curve end time from our graph. And to do that, we can use the fact that the animation class allows this type of array indexing to get its keyframes. So I'm saying I want to get the number of keyframes in our bob curve, and we have to subtract 1 from that because of course arrays are 0 based. So we're saying get the last keyframe in your curve and give me the time of it. Now, like I said, at default, this will simply be the time 2 from this last keyframe. But if we change that curve, we want this code to work irrespective. And that's all that our initialize function has to do. So now let's have a look at the function that's going to do all the work of updating those playheads. It's called getVectorOffset, and it's going to be this function that is going to be called every frame by our FPS controller. The getVectorOffset function takes the speed that our character controller is currently going and will return a 3D vector. This 3D vector is actually going to describe an offset which we can then add on to the local space position of our camera. The first thing we're going to do is we're going to increment the X playhead. Remember, the X playhead is responsible for horizontal head bobbing, and the head is going to start at 0, but we're going to add on to it each time the speed that we were passed in. This is the speed we're currently going, but of course we need to scale that by time.delta time because speed is a per second value, and we want to find out just how much to update the playhead for this particular time slice, this particular frame. So that updates our playhead, but it gives us no control over how speed is going to be mapped to the speed at which we move along the horizontal axis of our graph. So we simply do divide by base interval. Despite what I said just now, actually it's the other way around, okay? The bigger the base interval is, the slower we will move along our timeline. So the speed at which our playhead moves is now dependent on the speed of our character controller, but we also have this base interval value as a kind of master speed control. Next, we want to do exactly the same to the Y playhead. So as you can see, we add on to its speed times time.delta time divided by base interval. But we then do an additional multiply to multiply it by that vertical to horizontal speed ratio. Remember, this is our way of describing how fast the Y playhead should move compared to the X playhead. And you're reminded that we currently set this to 2, okay? So our Y playhead, which is ultimately going to be responsible for evaluating the speed at which our head bobs up and down, is going to move along the horizontal axis of the curve twice as quickly as the X playhead. So because we've incremented our playheads, we need to make sure that we haven't moved them past the end time of the curve. If we end up with a playhead that's greater than, let's say, 2, assuming we don't change the length or shape of this curve in the inspector, then we need to wrap it back round again. So as you can see, I say if X playhead is greater than the last time in our curve, then simply subtract the curve end time from our playhead, and we do the same for the Y playhead as well. Okay, so now let's actually evaluate the X offset. So to do that, we create a local float called X position or XPOS, and we use the animation curves evaluate function, passing in our X playhead, so that if we look at our sample, if we imagine our X playhead was in the middle, it would actually return this value here at the very bottom of this curve. And finally, we multiply it by the horizontal multiplier. Remember, this is the thing that takes the value that we get back from the sine curve, which might be in the +1 to -1 range, and in our case, it's going to scale it right down so it's in the -0.01 to +0.01 range. So it allows us control over how big the bob is going to be. And of course, we're going to do exactly the same for the vertical movement of our head. We say YPOS equals, and then we evaluate our curve again, but this time using the Y playhead, and this time multiplying it by the vertical multiplier, which you're reminded is twice as big in this case. We want very subtle horizontal movement of the head, but a little more dramatic vertical movement of the head. So now we have exactly how much we wish to offset the camera horizontally and vertically. Now let's just pack them into a vector and return it from the function. And of course we don't want any forwards or backwards head bobbing, or we might look a little bit like a chicken. So we just set the Z component of this vector to 0. This vector here is what we can add in our FPS controller class to the local space position of our camera, and we will now have successful head bobbing. And that is our curve controlled bob class complete. So what we need to do now is we need to create an instance of this class in our FPS controller. So this will be a serialized field, and it's going to be a private variable of type curve controlled bob, and I'm going to call this head bob. I say new curve controlled bob, and there. If I save that off now, first of all to check if I haven't got any errors, and I haven't, and if I select our FPS controller rig now, you can see we now have the head bob showing up in the FPS controller inspector. When I open that up, hey, there are our values that we can use to control the bob extents and the bob speed. And if we click on the graphical representation of that curve, it's going to open up the curve editor, allowing us to tweak the shape of the curve. Now, as you can see, it's not exactly the sine wave, because in order to do that, I'd need to rotate that around like so. But I actually quite like it having this kind of plateau in the middle, because a pure sine wave tends to look a little bit predictable and robotic. So this way, which by the way happens by total accident, that's just how it's set the middle point. So it has that plateau, but I like it, so I'm going to leave it like that. Okay, so now our FPS controller has the head bob helper class. Let's see how it's used to make our camera bounce up and down. So we've now added that curve controlled bob member called head bob to our FPS controller. But one of the other things we're going to need to do in our startup function is record what the initial local space position of our camera is. That's its position relative to its parent game object that contains the character controller. And the reason we need to do this is because you will remember that I said that every single frame our FPS controller is going to call the head bob's get vector offset function, which is going to retrieve a vector 3 that contains a local space offset with which we can adjust the local position of the camera. Now we could of course just every frame take the vector that this function returns and add it to the local space position of our camera, because of course it's a modulating pattern. But we can't really do that because floating point numbers have limited precision on computers, and over time, when we perform arithmetic on them, these floating point inaccuracies can accumulate. And if we left our head bobbing for many hours, we could come back and see that these errors had crept in over a long period of time, enough such that the head had actually bobbed off of the shoulders and was no longer in its original position. So what we need to do to counteract this is, at scene startup, we will record what the local space position of the camera was then, and then every single frame, once we fetch this offset vector, we will then add it on to that original startup vector, so that we're always regenerating a fresh offset from the original vector that we started with at the beginning of the scene. So in order to do that, we will go down to our private variables block, and I will add a new private vector 3 called local space camera pos, and by default I'll just set it to vector 3.0. Why not? And then in our start function, just under where we grabbed a reference to the main camera in the scene, we will say local space camera pos equals camera.transform.local position. And there you go. Now every frame we can generate our offset from this vector, so we don't get any rounding errors creeping in over time. Okay, so next up we need to call our head bob's initialization function, and you'll remember that the initialize function takes a base interval value, and we said that this base interval value is essentially our way of controlling the speed at which our playheads move across the animation curve. Quite literally, you can think of it as the interval between head bobs. The longer it is, the more slowly each bob will occur. I was originally going to do this in the same way that Unity does it with its first-person controller script, and that was, I was going to make the base interval a member of the FPS controller class, and I was going to call it step interval, and it was that step interval that I was going to pass into this initialize function so that it will use it to control the speed at which our head bobs. And the reason I was going to make this a member of the FPS controller class and not a member of the curve controlled bob class, where it seems it would make more sense, because I was originally going to implement the footstep system very similar to what Unity's standard asset script does, and that was reuse that step interval value to also space apart the playing back of footstep sound effects. However, literally while I've been recording this video, I've just thought of a much better way to do this and have much better synchronization between the footstep sound effects and our head bob curve. If we look at our animation curve in the inspector, we can imagine that it's probably when the curve reaches its lowest point here that we want a footstep to happen. And we can see it's also at 1.5 seconds along the timeline. Wouldn't it be great is, instead of having a completely disjoint system that tries to match up the sound effects with the head bobbing action and probably not getting very close to it, if the curve controlled bob class itself allowed us to register callback functions with it anywhere along its timeline. So for example, our FPS controller could say to our curve controlled bob class, I want to register a function when the playheads reach 1.5 along your timeline. As the playheads loop around and repeatedly pass this 1.5 second mark on the animation curve's timeline, it would call that function that was registered with it. Using this system, we have perfect synchronization between the shape of our curve, and we can choose precisely where we want the footsteps to happen. Like I said, with our curve, I think we're going to want it to happen at the 1.5 second mark. But we'll also support the registration of multiple events along the timeline. So we could have a much longer curve that was maybe 10 seconds long that didn't repeat so quickly, and we could register different footstep events along its timeline. So I'm not going to implement that right now, okay? We are going to implement it in this lesson, but not quite yet. And the only reason I bring it up now is because we're going to implement this system, I actually no longer need this base interval to be passed in as a parameter to the initialize function. It might as well now just live in the curve controlled bob and show up in its inspector, because we no longer have to reuse this value between two systems. The curve controlled bob class is going to handle it all. It's going to handle the head bob, and it's going to handle the triggering of sound effects or whatever event functions we want to register with it along its timeline. So I'm going to remove that parameter now from the initialize function. I'm going to remove that code where we assign that parameter to our base interval, and I'm going to move the base interval member up into my serialized block of variables so it shows up in the inspector. And of course I have to add this serialized field attribute, and I'll set it to 1 by default. And we can now see that if I go back to the editor the base interval now shows up as a member of our head bob class, and simply by moving that up and down we can slow down and speed up our head bob respectively. And because the playback of our sound effects are going to be linked to this curve, when we increase or decrease that base interval, it's also going to increase and decrease the frequency at which our footstep sound effects are played. The other thing we should probably add to our initialize function actually is the resetting of the playheads back to 0, just so that if we've got a curve controlled bob object that we've used already and we just want to reset it back to 0, calling initialize again will do that. So resetting these playheads to 0 will allow us to reuse our curve controlled bob object just by calling its initialize function again. Okay, so now we're going to go down to the bottom of the start function of our FPS controller, and we're now going to make sure that we call the initialize function of our head bob object. So I will say headbob.initialize. Okay, so next I'm going to scroll down to the very bottom of my fixed update function. Okay guys, right underneath here where we finally move the character controller, and it's here that we're going to call our headbob's get vector offset function, and we're going to pass in the speed that our character controller is currently going, and with the vector that we get back we're going to set the new local space position of our camera. So the code's going to look something like this. So we don't want to perform a head bob if we're not moving. So the first thing we do is we use the velocity property of the character controller. That's going to return a 3D vector describing the speed and direction that our character controller is moving. And if we get its length and find that it's more than 0.01, then yes, it is moving at some speed. So we do want to perform a head bob. So if it is moving, then we need to set the new local position of our camera. And we will set that to that local space camera position. Remember, this was the position of the camera at scene startup, so we're making sure that we always reset it back to what it was at the very beginning before we add the vector offset onto it, and then we add onto that a call to our headbob's get vector offset function, and you can see that we pass in as the speed the magnitude of our character controller's velocity. If we're not moving, however, we'll just make sure that we set the camera position back to what it was at scene startup, just so we make sure we never get any floating point drift of the camera. So if we run that now, it should work, although it won't look tremendous at the moment. We're going to fix that in a minute. So let's have a look, check we haven't got any errors. So we need to exaggerate the head bob a little bit just so we can see what's going on. So for now I will make the vertical head bob 0.03, and I'll also maximize the screen so we can see what's happening. There you go. Walking, you can see we have some head bob. Hopefully that's picking up on the camera. Walking looks fine. I've got no problem with walking. Looks pretty good. You'll notice running though looks far too fast. We're bobbing up and down, of course, based on speed. But of course, in the real world, just because you're running twice as fast as you walk doesn't mean that your head needs to bob up and down twice as fast, because when we're running, we normally take longer strides. So what we need is an extra control that basically just manipulates the speed that we send into the get vector offset function when we're running. So in our case, for example, where we have our walk speed at 2 and our run speed at 4.5, we don't necessarily want the ratio between our walk speed and our run speed to be directly reflected in our head bobbing speeds. We might say when we're at running speed that our head bob should only be 1.5 times what it is when we're at walking speed. So I'm going to add a new member to our FPS controller called run step lengthen, and this is going to be used precisely for that purpose. When we send in our speed into the get vector offset function, we'll just say if we're walking, then just send in this value unaltered. But if we're running, then send in our magnitude multiplied by this factor. So let's go up to the variable declarations of our FPS controller and add that now. So I'll put that under here, and I will make it another serialized field. It's a private float, and it's going to be called run step lengthen. Now I'm going to set this by default to 0.5, which probably will work out all right. Maybe 0.75. Okay, so we're going to slightly slow the speed down artificially just as we add it into our get vector offset function. So we're going to just say when we're running, we want to just slow the bob down a little bit, so it's not purely based on our actual speed, but we're pretending that our speed is kind of 75% of what it actually is. So in order to do that, when we send the speed into our get vector offset function, we will simply multiply it by this. We will say if we're walking, just multiply it by 1. In other words, do nothing to it. But if we're not, then it means we're running. Well, then we will multiply our speed by that run step lengthen value, like so. And there we have it. So let's see what that looks like. And hopefully when we run, our head bob won't be quite as fast when we're running. Here we are walking. Looks about right. Actually, let me call up the scene view as well, so we can actually see the camera moving up and down, because that might be a worthwhile test. So we can see our camera bobbing up and down there. And then when we run, what does that look like in the game view? Doesn't look too bad. It might still be a little bit too quick, so maybe I'll turn that down to 0.65 here. So there's our walk speed. Yeah, I think that's better. I think that's a better run speed. Let's have a look again in the scene view. There's our walk. There's our run. That looks more like it. If you see the camera bobbing up and down, look, that looks about right for run. So if we had footsteps in there, we'd be going boom, 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 boom. But walking, it would go clop, 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 clop. Yeah. Hope you enjoy my sound effects there. Okay, so phase one of our head bobbing system is complete. Of course, we can really ramp up these values. If I put a vertical multiplier up to 0.13 and horizontal multiplier to 0.11, we're going to get a lot of horizontal and vertical. Hey, look at that! Dun, 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 dun. That's pretty extreme. And then when we run, it's quite good actually to over exaggerate it while you're just testing what to have the run step lengthen value set to, because I think that's probably about right for the run. About that, yeah. But of course we want it to be much, much, much more subtle than that. So here we are. If you look at the wall next to us, it looks about right to me. As we walk past that security department sign, you can kind of see it bobbing up and down as we walk. See it kind of bobbing up and down a bit more quickly as we run. Once we've got some footsteps in there, it will really make the effect much more complete. So now that our basic head bob class is working, let's now expand it with that system we just talked about. The ability for any object to register a function with the head bob class such that it's called at specific points along the animation curve's timeline. So we're going to go back to monodevelop, and the first thing we're going to add to the top of the file is using system.collections.generic. That's because we're going to use the C# generic list. So what types of events should we be able to register with our curve controlled bob class? Well, we currently have two types, those that should be processed by the X playhead, horizontal events, and those that should be processed by the Y playhead, vertical events. In this particular demo, we're actually only going to use vertical events because we just want to trap when the head is moving up and down, and when it's at its lowest point, play a footstep sound. So we're going to create a public enumeration to represent the type of event that it is, and I've called this enumeration curve controlled bob callback type. And a callback can either be a horizontal or a vertical callback, describing whether it should be processed by the X playhead or the Y playhead respectively. Next up, we want to define the delegate that's going to be used to describe the type of callback function that we wish to store in our curve controlled bob class. I call this delegate curve controlled bob callback. Variables of this type can be used to reference a function that has a void return type and takes no parameters. But of course, an event needs more information than just the reference to a function to call when that event happens. It needs a time that the event should happen, and of course it needs to also store the type of callback event that it is. Is it a horizontal or is it a vertical event? So we're actually going to create a new class that will store the time that the event is supposed to happen, a reference to the function that should be called when the event happens, and the type of callback that it is, whether it should be processed by the X playhead or the Y playhead. I've called this class curve controlled bob event. Once again, because we want the data that we store in here to be saved and serialized along with the parent curve controlled bob class, we use the system.serializable modifier. So this class is going to have three members. So the first variable is going to be a public float called time. Simply put, it's going to store the time along the x-axis of the curve that we would like this event to be triggered. Next up, we need to actually store a reference to the callback function itself. So this needs to be a variable of type curve controlled bob callback, which I've called function. Remember, this is our delegate. It describes a reference to a function that has a void return type and takes no parameters. Finally, we need to store the type of callback it is. Of course, this needs to be a member of our curve controlled bob callback type enumeration, and by default I set this to curve controlled bob callback type vertical, and in fact that's the only one that I'm going to be using probably, as I don't want any sound effects or anything to happen based on the horizontal movement of the head, just the vertical movement. Okay, so now that we have this curve controlled bob event class which represents a single event on our timeline, we now need to create a list where we can store all of the events that may be registered. So as you can see, I've created a private list that will store curve controlled bob event objects. Remember, that's our event class up here. And you'll also notice now that I've added two more floats called previous X playhead and previous Y playhead. That's because we're going to need to know where the playheads were on the previous frame and where they are on this frame, and we need to see whether we've passed over an event that should have happened in between those times, because we might not always land squarely on an event's time. So we need to make sure that if the previous position of our head was before an event and the current position is now past that event, then we need to trigger that event now. So that's why we have the previous X and the previous Y playheads, and in our initialize function we should probably set those to 0 as well, like so. Okay, so the next thing we need to do is we need to create a registration function so that our FPS controller script, or indeed any script anywhere in our application, can contact our curve controlled bob class and can say, hey, I want to register a function with you to be called at this specific time by this specific playhead, and I'm going to call this function register event callback, and it takes three parameters. It takes the time that we would like to register the event for, and like I said, this should fall within the keyframes on your animation curve. We also pass a reference to the function that we would like to be called at this time. So remember, this should be a function that takes no parameters and returns a void return type. And we also pass in a member of the curve controlled bob callback type enumeration. And of course, in this function, we create a new object of type curve controlled bob event. We copy over the time, the callback function, and the type that was passed into this function so that we store them in that curve controlled bob event. And of course, now what we need to do is we need to add them to our events list. So we will say events.add. So if we had lots of scripts calling this function at scene startup, we shouldn't really rely on the fact that all of these events would be registered in the correct time ascending order. So what we should probably do whenever an event is added is we should just sort the list. So we have at the top of the list those with the smallest time, and at the end of the list those with the largest time. Otherwise we're going to get into real problems trying to step through and process events as we move the playheads. Now of course, what we want to do is tell our list to be sorted, but because our list contains curve controlled bob event objects, the C# list class has no idea how to sort objects of this type. It's an object that we've made up ourselves. So what we need to do is use a version of the C# list's sort function that allows us to supply our own function that describes how two objects in the list should be compared. So I'm sure you've seen stuff like this a million times before. We're using an anonymous function there, okay? It hasn't even got a name. We're just kind of defining the function in line. It's called an anonymous method. And the sort function expects to take a function that returns an integer and takes two parameters of type t, where t is the type stored in the list. And we basically have to return a value smaller than 1 if t1 is less than t2. We have to return 0 if t1 is equal to t2, and we have to return larger than 1 if t1 is greater than t2. And we're using the float's compare to function to do this, which will automatically handle that for us. So if you imagine when the generic list is being sorted, whenever it finds two elements in the list and it needs to know how to compare them, it will call this function. It will pass our function the two elements in the list, and we in this function will tell the list whether the time of t1 should be placed higher up or lower down the list than the time of t2. And if we wanted this to work the other way around, if we wanted to store times in descending order, we would actually do the compare t2.time compare to t1.time. We would flip around the arguments, and that would give you a descending sorted list by time. So there you go, that's how you pass the comparison delegate into the C# generic lists sort function. Okay, so now it's time to do the actual event processing. So in our getVectorOffset function, we're going to need to iterate through all the events and process them. See if any of them are falling between the previous playhead position and the current playhead position. And of course, we've got events that might have to be processed for both playheads. So we'll set up a loop to loop through all of the events in our list. We'll fetch the event from the list that we're currently processing, and assuming it's not null, we'll see if it's a vertical or a horizontal event, and we'll process them differently, obviously, because we need to use different playheads. So let's look at the code for processing the vertical playhead first. So if the events type is curve controlled bob callback type vertical, then we need to trigger the function stored in this event if two conditions are true, basically. Firstly, if the event time is greater than the previous playhead position and smaller or equal to the current playhead position, that means it lies exactly in between where our playhead was last frame and where it is this frame. So we'll say if the previous Y playhead's position is smaller than this event's time and the playhead's current position is larger or equal to the event's time, well then we know that that event is bang smack in between the two playhead positions, the previous one and the current one. So that function must be called. But there's also another case we have to handle, because obviously once the time goes past the end of our animation curve, it wraps around. So we could be in a situation where in the last frame we had, let's say, the previous playhead at 1.8, and let's say the length of the animation curve was 2, and then the next playhead position might have already wrapped around and be smaller on the timeline than the previous playhead. So what we need to do in those particular cases is we need to say, or if the previous playhead position is larger than the current playhead position, well that means that we've wrapped around from where we were in the last frame, so we've got a previous playhead position at the end of the animation curve and our current playhead position is at the beginning of the animation curve, and either the event time is larger than the previous playhead position at the far end of the curve, or the event time is smaller or equal to our current playhead position at the beginning of the curve. Okay, you got that? You might have to draw it out on paper just to get it in your head. So assuming any of these conditions in the brackets are true, we need to call that callback function. And we do that by simply saying ev.function, which remember is the variable that stores the reference to our function, and we have to put those parentheses on it because our callback function takes no parameters. So there you go, that's just calling all of the functions that have been registered for the vertical playhead. So of course now we have to do pretty much exactly the same thing, but this time for processing the event type if it's a horizontal playhead event. So as you can see, it's exactly the same, just a copy and paste, except this time we change all the Y's to X's. Let me just check I have changed all the Y's to X's. Looks like I have. Okay, so after we've processed this code block, all of our callback events will have been triggered. So we just need to make sure at the end of the function we record the X and Y playhead positions in the previous X and Y playhead positions so that they can be used in the next update. And that is our event registration system added to our curve controlled Bob class. But of course we haven't really got anything that we can test with it yet, have we? So we're going to have to, I think, just put a few audio sources on our character controller just so that we can check that a sound will be played if we register a callback function with it. But please don't think that what I'm going to do now is the real sound system that we're going to implement. All right, this is just placeholder stuff to check that our curve controlled Bob class is working correctly. Check that's saved off. I'm going to go back to the editor. Okay, so in order to test that our head bob callback system is going to work, what I'm going to do is I'm going to add two audio sources just temporarily to our first person controller. Okay, so I'm going to choose audio source, and then I'm going to add another audio source. So there you go, two audio sources. I'm also going to make sure for now, I'm not worried about 3D positional audio. I'm just going to make sure that the spatial blend slider is set all the way down to 2D on both of those, right? So it's just a 2D sound. I'm also going to untick both of the play on awake properties in each of those audio sources. So what I want to do is I just want to temporarily put some sounds in these two audio sources so that every time a event is triggered to play a footstep sound, we'll just play that one, then we'll play that one, then we'll play that one. We'll just ping pong between the two. So because we have the standard assets imported, and in particular we have that characters folder, I think you'll find there is in the first person character folder some footstep sounds. So if you can't find that folder, and you want to do a search, just type foot in the project window search bar, and I'm just going to drag footstep 1 audio into our first audio source and footstep 2 audio into our second audio source. Okay, now if you haven't got these footstep sounds in your project, you can import them by going to the assets menu, input package, and choosing characters. But to be honest, we're not going to be keeping this stuff anyway. It's just real temporary stuff to make sure this works. So you could use any sound. You could use bouncing balls, springs, or you could just use you talking into a microphone going left, right, left, right, left, right, like that. Okay, so we've added some audio sources and some audio clips to those audio sources, and like I said, we're going to ping pong between them whenever a callback is called. But because we turned off the main camera in our scene and we've got this new main camera now, which is on our character rig, we need to make sure that we have an audio listener added to it. Okay, because the only audio listener in our scene at the moment is on our previous main camera, which has now been disabled. And without an audio listener, well, it's like a head without ears, folks. You can't hear anything. So let's add the audio listener. That's all we need to do. And of course, we now need to go back to our FPS controller class. We need to register a callback function with our head bob, and we need to just put a little bit of temporary code in place to ping pong between those two audio sources. In other words, which one to use whenever that callback is called. So in our FPS controller class, I'm just going to put all of this stuff like right at the top, just to remind myself that this is all temporary shit that has to go. Okay, so the first thing I'm going to do is I'm going to create a public list that we can store our two audio source references in. Alright, so as you can see, public list that will store audio sources, and I've called it quite imaginatively audio sources. If I save this off now, just go back to the editor, we're going to see in our FPS controller at the top, we've got this audio sources drop down. Let's just put 2 elements in there so we get 2 slots where we can then drag over both of our audio sources into there. There you go. So now our FPS controller has access to both of those audio sources and the audio clips that they have been assigned. I'll also create another private variable here that is of type int, and I'll call this audio to use. I'll set it to 0. This is basically just going to be flicking between 0 and 1. It's going to be used as the index to fetch the audio source from this list. So we're going to start off playing audio source 0, which is our first footstep sound, and then once we've done that, we're going to increment it to 1, and then the next time we get a callback request, we're going to play the second audio source, and then goes back to the first one, and so on. So now let's go down to the bottom of the class and create a function that we can register as a callback with our curve controlled bob class. So the callback function obviously has to have a void return type, and I'm going to call this play footstep sound. And of course, we know that the callback function must also take no parameters, and what we'll do in here is we will just simply fetch the audio source from the list. So we will say audio sources, then we'll use our audio to use integer, and we will tell it to play its sound. So the first time this function is going to be called, audio to use will be 0, and it will play the first clip in the first audio source, this one here. Then of course we just need to make sure whenever it's played a sound, we basically say audio to use equals, then we'll say if audio to use equals 0, then audio to use should equal 1, else it should equal 0. In other words, if it's 1, it should equal 0. If it's 0, it should equal 1. Okay, so we have the function that should be called to play our sound effects. All we need to do now is register this at the correct time within our animation curve. So in our start function, just after we've initialized our head bob, we will say head bob dot register event callback, and the what time did we say we wanted to register it at? I think it was there you go, 1.5. okay, so 1.5 along the timeline is where we want that footstep to play. So into our register event callback, the first parameter is the time, which we know is 1.5. The second parameter is the name of our callback function, which is play footstep sound, and the third parameter is of type curve controlled bob callback type. So we will pass in curve controlled bob callback type vertical. Okay, so we've registered a function called play footstep sound that is going to be triggered every time the vertical playhead, the Y playhead, passes the 1.5 seconds mark on the animation curve. Shall we see if this works? Now before I press play, let me just preface this by saying, remember, this is going to sound pretty crappy because we've only got 2 footsteps. The actual footstep sounds aren't very good anyway. In the real game, what I'll probably do, and I haven't actually written this system yet, but this is what I'm thinking. I'm thinking I'm going to have some kind of environment audio manager, okay, where we would store sounds by theme. So we might have a collection of footsteps that apply to the character walking on metal plates or a tin floor. We might have another collection of footsteps that would be played when the character is walking on concrete or walking through water, etc. Whatever surface we're on will generate different footstep sounds, and we would be selecting from a much larger pool of footsteps than just 2, because when you just have 2 footsteps, you just hear this clip clop, clip clop, clip clop sound, and we need to have a much bigger pool so that every single footstep sounds like it's different. It won't be, but if you have a large enough pool, maybe 6 or 7 different footstep sounds, that will be more than enough to shake off any pattern that the user might think they can hear. So like I said, this is going to be a bit clip-cloppy, but it's just to demonstrate that it works. Hey, look at that. It does indeed. And the run works too. And if I'm shouting, I'm sorry. It's just I've got headphones on to record this, and those footsteps are freaking loud, man. They're taking my head out. They're literally taking my ears out. Okay. So there you go. Of course, the great thing about this is that event registration system could be used, for anything. And in fact, it's a really good template to use for not just the head bob system, but any type of curve controlled thing that you might want to implement in the future. I use callback systems like this all the time. In GI Racing, for example, I use it for the camera system so that when cameras change, various things in the scene can be notified. Okay, so that's our head bob system done. For now, I will leave those footsteps in place in this code just so you can test it. But I am going to be deleting all of this, okay? I'm going to be getting rid of those 2 members that we added, the list and the audio to use. And I'll also be getting rid of this, eventually anyway, this play footstep sound function. Because we're going to be doing something much better than that in the actual game. But I'll leave it in there for now so that the scripts that you download from the zip file accompanying this lesson still has it in there, so it'll be easy for you to test. Okay, so what next? Why don't we add crouch functionality to our controller? Now remember, I said earlier on in this lesson that when we crouch, we can't just move the camera down. What we need to do is physically resize the height of our character controller's collider. And I think what I'm going to do is I'm going to pretty much cut it in half. So at the moment we're at 1.8, so I set it to 0.9, that's what it's going to look like. But of course, if I just resize the collider, it's still in the air, the camera hasn't moved down. All that happens is our collider is floating. However, you will also remember that not only do we have gravity affecting our collider, but we also have that stick to ground force that's going to push our collider down such that it sticks on the ground. So all we really have to do is just resize the collider and it should go boomf down on the ground like so. So let's put it back to 1.8. What I'm also going to do, guys, is at the scene startup, I'm going to record what the initial height of the collider is, okay? And then when we set the height, rather than just saying if we're crouching, divide it by 2, and if we're standing, then multiply it by 2, I don't want those floating point accumulation errors to creep in, or we could end up with a capsule after many hours that is not even remotely 1.8 when we're stood up. So we're just going to make sure that we record what the initial original height of our collider was in its standing pose at scene startup, so we can always resize from that reference. Before we do anything though, we need to add a crouch button, and our input manager doesn't currently have one configured. So we're going to go to the edit menu, we're going to go to the project settings menu, and I'm going to call up the input inspector. As you can see, we currently have 18 axes in our input manager, but we don't have one called crouch. So let's add a new one now by changing the size of the axes array in the input manager for 18 to 19. This will create a new entry which will inherit the properties of what was previously the last entry in the axis list. So you can see it's added another one on the end called cancel. I need to rename that crouch like so, and I need to change the key that is going to be pressed to activate it, because I want it to be the left control key, and in input manager talk that is left CTRL like so. We also want to get rid of the alternative button which is set to joystick button 1. We don't want that, and just check that you have type on key or mouse button. Alright guys, very important. Okay, so if we save that off and now open up our FPS controller script in MonoDevelop, the first thing we need to do is add a new member to our player move status enumeration, because we don't currently have anything in there to identify that our controller is in a crouching state. So as you can see, I have just added crouching in there. Okay, next up we're going to need to add some variables to our first person controller. We're going to need to add a crouch speed. So as you can see, I've added that underneath the walk speed, run speed and jump speed. I'm going to set the crouch speed to 1 by default. Now originally I had walk speed set to 1, but that was too slow when I tried it in the editor, and I ended up changing it in the inspector to 2. So we're going to have the walk speed at 2 and the crouch speed at 1. And we're also going to want to create a float that's going to store the original height of the character controller at scene startup. So we'll do that down here in our private members block. So you can see I've created a private float called controller height, set it to 0 by default because we're going to set this up in the start function. We're going to query the controller's height property and store that in there. And we probably also need a boolean that we can ask if we are currently crouching. So there you go, I've added a new boolean called isCrouching set to false by default. Okay, so in our start function, right underneath where we grab the character controller component, what we'll do is we'll fetch the height of the character controller before we've messed around with it and put it into or out of crouch mode, and we'll store it in our new controller height private member. As you can see, I say controller height equals character controller dot height. Remember, you can check out the character controller class in Unity scripting reference to see all of the properties and functions that it exposes. Okay, so now if we go down into the update function, we probably want to say that if the jump button is pressed, then we're not allowed to jump if we're currently crouching. We shouldn't be able to go from a crouch straight into a jump. So let's modify that and say if the jump button isn't pressed and we're not crouching, then process the jump request. Okay, next up, let's see if the crouch button is being pressed. And of course, we're going to do that by using the input.getButtonDown function, but this time passing in the axis name crouch. And you can see I say if the crouch button has been pressed in this frame update, but then what we need is to toggle the state of whether we're currently crouched or not. So in other words, if we're crouching, then we're going to put it into an uncrouched state, and if we're not crouched, we're going to put ourselves into a crouch state. So we can do that by simply saying is crouching equals not is crouching. And of course, if we are crouching, then we want to set the height of our character controller to half the normal height. But if we're not crouching, we want to set it back to the normal height that we stored in our start function. So I say character controller dot height equals, if we are crouching, then set it to the controller height divided by 2. Otherwise, just set it back to the original controller height, which in our level is 1.8 meters. Okay, so if I move down to the bottom of the update function, you can see we have this series of conditionals where we're basically trying to set the current state of the controller. So we say, if we've just landed, then set ourselves to the landing state. Else, if we're not currently on the ground, then set ourselves to the not grounded state. Otherwise, if we're not moving at all, set ourselves to the not moving state. We then say else, if we're walking, set ourselves to the walking state. Else, set ourselves to the running state. So we want to put something else in there now that says before we check if we're walking, let's check if we're crouching first of all, because that state is going to take precedent. So I will say if we're not moving, then the next thing I'll check is are we crouching, and if we are crouching, set the movement status to player move status dot crouching. Else, if we're walking, set it to walking. And then finally, if none of the above are true, then it means we must be running. And that's our update function done. So now we need to go down into our fixed update function, and we need to calculate the speed, because at the moment we basically calculate the speed as saying if we're walking, then set our speed to the walk speed, else set our speed to the run speed. What we want to do is make this slightly more convoluted again and do the following. We want to say if we're crouching, then set it to the crouch speed, else if we're walking, set it to the walk speed, else set it to the run speed. It's two conditionals in one using that kind of shorthand approach. So that should probably work. Let's try it. Okay, so I'm going to crouch. So the first thing you'll notice is that when we drop to the floor, we get a footstep sound. Now the reason why that is, I'll show you in a minute. Don't worry about that for now. We'll fix that in a minute. But I also don't like the fact that we're getting the standard footstep sound while we're crouching. Now, of course, in our actual production code, what will happen in our footstep sound callback is we will play different sound effects based on whether we're walking, running, or crawling. So, when we're crawling, we'll probably have more of a foot scraping along the ground, much quieter sound effect. When we're walking, it will just be a regular walk sound. And when we're running, it'll probably be a much heavier sound. At the moment, we don't have those sound resources to hand. So I think what I'm going to do do is I'm going to say if we're crouching, then just don't play a sound at all for now. So let me save that off, go back to the editor, see if that kills the yes, it kills the crouching sound, but I haven't really fixed the problem, right? The only reason we're not getting that footstep sound now when we crouch is because, and you'll notice there, we did still get it when we stood up. Sometimes. There you go. We got it sometimes when we stood up. So just to make it a little bit more clear, to see if we fix the problem, I'll temporarily remove that premature return from the play footstep sound function. So we do once again get that footstep sound when we crouch, okay? Because we're not fixing it there, we're just hiding it by not playing a sound when we crouch. And at the moment, although I don't want a footstep sound when I'm crouching, what I don't want to do is later on when I add a proper crouch sound effect for my footsteps, then we're going to get that problem again. When we go into the crouching mode, we're going to get that stray footstep being played. Of course, the reason why this is happening is it's being triggered by our headbob class, and the reason it's being triggered by a headbob class is because you'll notice that what we do at the bottom of our fixed update is we get the speed of our controller and we send that speed into our getVectorOffset function, which we know is going to move the playheads of our animation curve inside the curve controlled bob class. The thing is, when we crouch, although we're stood on the spot, we actually move very, very quickly in a downwards direction. That's because in the case where we're falling, we're applying gravity, but in the case where we're just on the floor already, we are applying that stick to ground force, which is obviously moving the playhead along. Of course, what we want to do is say that the speed that we send into the getVectorOffset function should really only ever be horizontal speed along the x-axis or the z-axis of the world. So what we'll do to counteract this is we will create a new vector that is going to be our character controller's velocity flattened to the xz plane of the world. And we'll do that by creating a local vector3 variable, which I will call speedxz, and we'll just create a new vector3 where the x component is simply the x component of our character controller's velocity. The y component is 0. See what we're doing? We're completely zeroing out any up or down movement when we generate this flattened velocity vector. And of course you can probably guess what the third component is going to be set to. That's right, the character controller's velocity's z component. That was a mouthful. Okay, so now we have the velocity of our character controller flattened to the xz plane. We're going to be using this as the velocity test. So instead of saying character controller.velocity.magnitude, we will say speed xz.magnitude. And of course, when we call our getVectorOffset function, we currently pass in the speed of our character controller by passing in the magnitude of its velocity, but we will pass in the magnitude of its flattened velocity, speed xz.magnitude. Cool stuff. And that should fix that problem. So if I press crouch, if we haven't fixed the problem, we should still hear that footstep sound, but I'm willing to wager we will not. So let's walk a little bit. There's our footsteps. There you go. No erroneous stray sound being triggered. So we will now uncomment that code for the time being so that we can walk around in crouch mode and we will not get any footstep sounds. Okay, so we still have some problems with our code. Currently, when we send in the flattened velocity vector of our character controller into the headbob's getVectorOffset function, we scale it by either 1 if we're walking or the run step length multiplier if we're running. So we're not handling the crouching case here. So in the case where we're crouching or we're walking, we're not going to modify the speed at all. We'll just let the speed of our character controller dictate the speed of the head bob. So in the parentheses here, I will say if is crouching or is walking, then don't modify the speed that we send in. Only modify it with run step lengthen when we're actually running. Okay, so let me just non-maximize the game view so we can see what this looks like in the scene view, and we should see our camera drop to the floor. So there you go. When I press crouch, boomf. Now, of course, if you wanted to make this a little bit more drawn out, you could actually have the resizing of the character controller from its 1.8 default height down to the half height in a coroutine that did it over a second or two. But because we're essentially waiting a little bit for our character controller to drop to the floor once we resize it, I actually don't mind it. I actually think it doesn't need to have a coroutine drag out that crouch animation. So next up, let's sort out the problem of Zombie Jill running right through our character controller's collider. We saw earlier that if we tried to fix this by making the player layer collidable with the AI entity layer, which remember is the layer with Jill's capsule collider on, that it didn't actually have the desired result. What happened is we ended up standing on Jill's head. The reason why this is happening is because Zombie Jill is being driven around the world by a nav agent. Yes, the root motion from the animation is dictating the speed that our nav agent should move around the level, and in certain cases our states are overriding the rotation of Zombie Jill to have her face in the direction that we want her to, but it's still ultimately the nav agent that is updating the transform of Jill each frame. And the navigation system knows nothing about the physics system. It pays no attention whatsoever to colliders. So if the nav agent is telling Zombie Jill to run forward and there's a wall in front of her with a collider on it, she's going to walk right through that wall. Now of course this doesn't actually happen in our game because we build a navigation mesh, and the navigation mesh does factor in all of the walls and surfaces that are so steep to the ground plane that they are considered non-traversable. However, our character controller, which is dynamic, is not of course baked into the nav mesh, so the navigation system knows nothing about it and will not try to steer around it. So what we were seeing earlier when we did make the two layers collidable is we were seeing Zombie Jill's nav agent completely disregarding any colliders that might be in the scene and walking her forward into our character controller's collider. The navigation system knew nothing about this penetration. So what we saw earlier was Jill's nav agent blindly moving her right into our character controller. The navigation system knows nothing about our character controller's collider. Our character controller, however, is a physics object and it is aware that it has collided with Jill's collider. So what it tries to do is resolve that penetration. And of course we saw that it did this by moving our collider up such that we ended up stood on Jill's head. And that is not what I call a desirable resolution to the problem. The solution doesn't lie in colliders, it's actually much easier to solve than that. We simply have to make our character controller something that the navigation system does know about and will not let the nav agent penetrate. That would be another nav agent or a nav obstacle. So if we go to our character controller object and in its inspector choose to add a nav mesh obstacle, you can see that this will allow us to add a special type of bounding volume to our character that the nav system does know about. Now a box isn't a very good fit for our character, so in the nav mesh obstacles inspector we will change this from a box to a capsule. I'm then going to pull in the radius a little bit to say something like, I don't know, 0.3. The height isn't really important and we don't want to have the curve tick box ticked, okay? If we do that, then it will actually carve our position into the navigation mesh. This is a dynamic object, so we don't want that to happen. So now that we've added a nav mesh obstacle to our FPS controller rig, the navigation system will not allow Jill's nav agent to penetrate our nav obstacle. Furthermore, during patrol routes and things like that, where in our child states we're obeying the desired velocity of the nav agent, Zombie Jill will try to navigate around other obstacles and other agents. All we've done is added a nav mesh obstacle. What I'm also going to do is select that camera and I'm just going to bring the near plane in a little bit so I get less clipping when the zombie is really close to me. I've changed the near clip plane from 0.3 to 0.1. If I press play now, and let me maximize this, you will see that Zombie Jill will no longer be able to walk through me. There you go, she stopped at me. She cannot walk through me at all. And furthermore, I cannot walk through her either. You can see what's actually happening is I'm actually pushing her around. Now don't worry about the fact that she's just walking into us at the moment. We haven't developed the attack state yet. She has no idea what to do once she's caught me. But you can see we've utterly solved the problem and we are now a solid object as far as the navigation system and Zombie Jill is concerned. Okay then, so let's now add the flashlight to our character controller, or at least a rough simulation of what the final flashlight will be once we have our animating arms in the game. The flashlight in Dead Earth is really comprised of two parts. The visual part, which the zombie and AI system knows nothing about, and that's the actual light itself And the second part, which is a special trigger that will alert the zombie whenever it enters that trigger. And of course we want to align this trigger so that when we shine it at the zombie is going to enter our flashlight trigger, and the flashlight is going to register as the flashlight threat in its state machine. Let's work on the visual part first. So we're going to select our camera game object. Remember, this is a child of the FPS controller rig, and we're going to add the light to that. And the reason I'm adding the light to the camera is because the camera is the object that our mouse look script is going to move up and down when we look up in the sky, and we definitely want our flashlight rotating with our head, so everywhere we look the flashlight will follow us. So selecting the FPS camera game object, I'm going to right click and I'm going to choose to create a new light, and from the light menu I'm going to choose spotlight. I'm going to set the range of the spotlight to, I don't know, about 20 meters maybe. And I'm also going to open up the angle of the spotlight a little bit, something like that. What did I go for? 50. Let's do 60 degrees for now. And I'm going to change the color from white to more of a yellowy tint, so it looks more like an artificial light. Now at the moment our flashlight's going to look pretty lame because our scene is still far too light, and the reason it's light is a number of reasons. First of all, our lighting in the scene is too light, but second of all, none of the geometry in the scene is actually using the Unity 5 standard shader. It's all just using legacy shaders, and they've got environment maps on and things like that, so they're not really being properly lit by the Unity 5 pipeline. And in fact you can tell that even if I turn off all the light in the scene, these metal trims along these wall tops here will still kind of glow quite bright, because they're having color sampled from a completely separate and disjoint environment map. But don't worry about that. We've got enough, I think, to create something that at least shows off the spotlight. So to make our spotlight look a little bit better, we need to dim down the scene. So let's call up the lighting window. If you don't have this tab, you can call it up by going to the window menu and choosing lighting, like so. And I'm going to move the ambient sort of like right the way down to nothing. We want no ambient whatsoever. And then I'm going to select, I think, the only directional light we have in this scene, which is this one here, which is under our navigation example geometry game object. And I'm really going to kind of turn down the intensity of that as well. You can see even if I turn it right the way down, some of this geometry still glows a little bit. So there you go. I'm going to tint it a little bit blue as well, I think, so it looks a little bit more nighttime. That flashlight might be a little bit too yellowy. Yeah, something like that, I think. Okay, so let's just walk around the level with that and see what it looks like. Oh, it's kind of roughly in the right position, isn't it? I mean, in the actual game we'll use a much better effect. We'll probably use a sort of texture to make a much smoother fall off between the sort of inner cone angle and the outer cone angle, but this will do fine for now. So we have the visual element in place. The zombie knows nothing about light, so this won't aggravate our zombie at all. The visual element is just for the player, so he or she has the feeling that they are holding a flashlight and they can see where they're going. To make this something that our zombie can see, we need to add a trigger to it. Now I'm just going to use a box collider for this, and I'm going to have the box kind of oriented along the direction of our spotlight's cone. But if you wanted to get realistic about this, then really of course our collider should be cone shaped. But Unity doesn't have a cone shaped collider primitive, so if you wanted to do that you would have to go into a modeling package such as 3ds Max, create a cone mesh, import it into Unity, and then when added to the scene you could then create a mesh collider from it. That would then create a cone shaped mesh collider. You could then turn off or throw away completely the mesh renderer and the mesh filter, so you'd just be left with a conic collider. But like I said, we're just going to use a box. So I'm going to click on the add component button, I'm going to type box, and then I'm going to choose box collider. Now, of course, this is going to create a box collider at the actual light's position. So we want to kind of move the center point sort of halfway down the cone and then increase the size of it in the Z extents. So I'll try something like, I don't know, 7. So you can see that's moved it 7 along its local z-axis, and then I will make the length of the box 14, so you can see that it still starts where our player is, and it doesn't have to go all the way to the edge of the light's range, because we can say that towards the end of its range the light is attenuated, it's weaker, and therefore doesn't aggravate the zombie. So around about 14 meters is okay. We don't want a light that's going to be too sensitive, that's just going to aggravate every single zombie in the level if you just spun around with the torch. Now, of course, this is currently very, very thin, so we want to make it a bit bigger. I want to make a bigger box, so we will set the X and Y size of this box to, let's say, 5. Now, don't get me wrong, I know this isn't fitting the cone at all of our spotlight, but it doesn't really have to. It still gives a pretty good effect. And like I said, you can always use a cone collider if you really want to. Now, of course, this needs to be a trigger, so we're going to click the Is Trigger box. But more importantly, we need to make sure that our spotlight game object, the game object with our trigger on it, is set to the visual aggravator layer and is tagged with the flashlight tag. Remember, the visual aggravator layer and the flashlight tag is what our AI zombie state base class recognizes as being the player's flashlight and will make that a visual threat. So let's see if this works. We know that just outside of this room, Zombie Jill is going to be sort of standing there in idle. So let's see what happens if we shine this light on her. Absolutely nothing. And I know why. I know why. Because if we select Zombie Jill, and I did panic for a little bit there, you can see that we have her intelligence all the way down to 0. And a zombie with 0 intelligence will make no attempt whatsoever to try and ascertain the direction of a light that might be illuminating its local area. So let's put this all the way up to its very highest for now, so that we have the most intelligent zombie. And now see what happens when we shine this light on her. Hey look, she's coming at us. So let's try and shake her off a little bit. I'm looking in the scene view. There you go. If you look in the scene view, you can see she's currently lost me. What I really need is the ability to turn this on and off. What I'm hoping to do is I'm hoping to see her go to start feeding. So I'm not going to shine the light on her. Can you see her in the corner? She's feeding. I'm going to shine the light on her. Hey, what's that? Oh my God. It's a flashlight and she's coming. I need a way to turn this flashlight on and off. Oops, she's seen me again because I've shone the light in her head. Okay, seems to be working. Oh, by the way, guys, you might have noticed that my zombie is no longer patrolling with a jog and pursuing with a sprint. I've actually nudged all the speeds of the states down 1, so that in Zombie Jill's case, currently, for this lesson, she is patrolling at speed 1, the walk speed, and she is pursuing at speed 2, which was our original patrol speed. And the reason I did that in this lesson is because if I set her pursuit speed to 3, that sprint speed, it's actually really, really fast. It's much faster than our character controller can move, and as a result it becomes impossible to actually shake her off. So it's probably going to be too fast, that animation, in the actual game. And in fact, I'm actually thinking that what I might do much further down the road is I did a little test, and although we didn't have a lot of success with these 3 animations in the blend tree because walk didn't blend into jog very well, I noticed that jog and sprint do actually blend together very, very well. So what I might do is put these 2 back into a blend tree, and then we would be able to do things such as set the patrol speed or the pursuit speed, rather than just whole numbers like 2 or 3, to something like 2.25 or 2.75, and that would allow us to come up with a speed between jog and sprint that's just right for our game. So even if we have several zombies that use the same animator, if we set their speeds just slightly differently, then that will have one zombie more hunched over that's doing more of a zombie jog, and another one where it's more blended heavily with the sprint, and it will make everything look a little bit different. But we'll do this at another time, but of course you can feel free to go ahead and do this already. I'm sure you know enough about setting up blend trees and transitions to simply put these 2 states in a blend tree and create the transitions to and from that blend tree back into our idle state. But like I said, if you don't know how to do that, then I'll cover it later, don't worry about it. Okay, so the next thing I'm going to do is I'm going to add the ability to turn the spotlight on and off temporarily. Okay, now in the game this is obviously going to be handled completely differently, because we're going to have our first person arms that's going to have the flashlight mesh, if you like, and when we decide that we no longer want the flashlight on, we're going to see an animation play, the hand lowering, and it's only when we lower the hand that the torch is going to go off, and likewise after the hand is raised that we're going to turn it on again. But for now we'll just create a game object reference in our FPS controller so that we can drag and drop a reference to this light object, and then we can just toggle it on and off. So I'm going to open up my FPS controller script, and I'm going to create a new serialized field of type game object, and I'm going to call this flashlight. We'll set it to null by default, and if we save that off and go back to Unity, we'll then be able to drag our spotlight game object and drop it into that reference. There you go. So our FPS controller now has access to that flashlight. So what I can say is in our start function, assuming we have a valid reference to a flashlight, then we will say flashlight.setActive false. We'll start with the flashlight turned off, once of course I spell false correctly. So we'll now scroll down to the update function, and around about the place where we process the jump button and the crouch button, we'll check if the flashlight button is being pressed. Now we haven't created a button in the input manager called flashlight yet. We'll do that in a moment. So for now, let's just write the code. So we'll query the input manager and we'll call its get key down function to see if a button called flashlight in our input manager has been pressed to this frame. And if it has, and we have a valid reference to that flashlight game object, then what we'll do is we'll just toggle its active state. And we do that by saying flashlight.setActive, not flashlight.activeSelf. Remember, ActiveSelf tells us whether the object is currently enabled or disabled, and the setActive function enables or disables the object based on whether we pass true or false. So if the object was currently active, ActiveSelf would be set to true, and we would want to turn it off when we press the flashlight button. So we would say flashlight.setActive, ActiveSelf would be true, so not ActiveSelf would be false. We would be setting the active state of this object to false, and therefore disabling it. So if I save that off, and then we need to go back to the editor and go back to the input manager and add that flashlight button. So I'm going to go to the edit menu, the project settings menu, and call up the input manager. I'm going to change the size of the axes array from 19 to 20, like so. And with that new element that it's added on the end, I'm going to rename it flashlight, and I'm going to set the key to be the F key. Now if I save that off now and press play, the first thing that should happen, because in the start function we disable the game object, is we should start with our flashlight off. Okay, I've got an error and my flashlight isn't working. Oh, good grief. I've got a buttload of errors. Okay, what's happening here? It's saying argument exception input key named flashlight is unknown. Did I spell it wrong? Flashlight spelt right there. Let's look in the code. Flashlight spelt right. Oh, I see what I've done. Notice that when I called the input manager, I used the function get key down, not get button down, which is what it's supposed to be, because button is the thing that queries the result of an axis in the input manager, but get key down, well, there is no physical key on my keyboard called flashlight, obviously. So let's change that to get button down, and all should work. And when we run this, I'm going to show you two other problems that we need to solve as well with our zombie alerted state. It's forever in flux, and we're forever tweaking it based on our results. Okay, so here I am. I'm in the level. No flashlight. I turn the flashlight on. It works. So let's find Zombie Jill. You can see she's... Hopefully you can see this in the video because I've got the light off. She's in front of me. I turn the light on and she's like, oh my god, what's that? And then she comes running after me. And there she is chasing me. Okay, so the flashlight definitely works. Okay, so second test, there she is, eating her dinner on the ground. Okay, can you see her in front of me? She's feeding. Let's now put the light on her and see if it works again. Dun, dun, dun. Oh my word, where's that light coming from? And there she comes. Okay, so it seems to work, right? Only there are some problems. So let me show you what the problems are, and just so we can see things a little bit better in this test, I'm going to ramp up the ambient lighting, okay? I actually don't need the flashlight for this first test. Okay, so I'm going to run past Zombie Jill so I can get her chasing me, and then what I'm going to do is I'm going to run up here and I'm going to snake, so I'm going to jump to the left, jump to the right, and hide behind a building so she can no longer see me. And what she will do is go to the last known position, the last place that she saw me. What we do in the alerted state is when she gets to the target that was a visual threat, but that visual threat is no longer registering as a current threat, she just drops down into the alerted state and she doesn't pan left and right. And that's the problem. We want the zombie, when it's got to the last known position of a sound source or a visual threat, we don't just want it to stand there looking forward and just waiting there. We want it to look concerned, we want it to seek right, seek left, and many times when the zombie does that, the zombie will often pick up the player again as a visual target. So it makes the zombie seem a lot more intelligent. Okay, so let's go and have a look at the second problem. Whereas the first problem was kind of like a design flaw, I suppose. This next problem is actually a bit of a bug in our alerted state, which I overlooked. So there she is feeding, and we've already seen that if we shine the light on her, she reacts. She stands up and she comes at you. But look what happens if I turn the light on and then turn it off again once she gets upright. She reacts, I turn the flashlight off, she goes back to eating again. What she should do is she should say, hey, I just saw a light coming from somewhere, that's much more important than this food, I'm going to go and investigate the source of that light. But as you can see, she doesn't do it. So we need to figure out why that is too. So here I am once again in the alerted state, which is forever in flux during our development cycle. And I'm going to go down to the onUpdate function, and the troublesome piece of code is this code here. Because what it says is, after it assesses all the threats, just to remind you, it says if the current visual threat is the player, then just go straight into pursuit mode. And we say if we have an audio threat or we have a visual light threat, then we set that as the new target, okay? But then we don't return from the function. We come down here and we compare it against our current target and see if it's more important. But there's a bit of an oversight in this next line of code where I say if the zombie state machine's audio threat is none, in other words, we're not currently registering an audio threat, but the visual threat that we have is type food, well then what we're basically saying is food is the most important threat, let's set that target and pursue to that location. But of course what we're overlooking at the moment is, although we might not be registering any audio or visual threats, we might still have the last known location of a visual threat or an audio threat as our current target. So we only want to come down into this block and set the food as our visual threat and go to that location if we also haven't currently got a target that is more important than food. So we would also say, and if zombie state machine dot target type equals AI target type dot none. So what we're saying, there's no audio threats, all we can see is food, and assuming that we weren't currently on the way to a more pressing target, even if that other target was, some more food, then we're just gonna, go and eat this food. But if we have a target set, which is like the player or a sound source, then we're not gonna override this target. We're gonna carry on towards it. So that's the first problem solved. So if I go back to the editor now and lure Jill towards the food source, we should see that when we shine the torch on her and then turn the torch back off again, she shouldn't go back to the food. So you can see already she's not just going straight to the food source. She's making sure that she investigates the sound source first. So that was the first little evidence there that we have it working. So now let's shine the torch on her, then turn it off again, and you see she hasn't gone back to the food now. She's coming at us. She's looked around and she said, I think I know where that light is coming from. Okay, so problem 1 solved. Although technically that was problem 2. We're yet to solve problem 1. So here we are back in our alerted state, which is forever in flux, and I'm going to scroll down to the update function, just very briefly kind of step through what happens here. So remember, at the start of the function we check all of the visual and audio threat types, okay? And if we have a visual threat or an audio threat or whatever that is more important than our current target, then that is set as the target. Now we then enter this code here where we say if our current target type is an audio source or it's a flashlight, and this is the important bit, and we haven't reached the target yet, then that's where we do the whole turning on the spot thing. If it's within our threat angle threshold, we drop into pursuit mode, and it's also where we, increment the direction change timer and either seek left or right intelligently based on how intelligent our zombie is, or seek left and right randomly. But all of this code, which is essentially implementing what we want it to do, is currently only executed when we haven't reached our target. And then underneath that we have the else clause, which deals with the case where the target is a waypoint. Once again, calculates the angle. If we're in the turn on angle threshold, then it goes into patrol mode. Otherwise, it seeks left or right depending on the angle to that waypoint. So what we don't have yet is something that handles the case where our target type is an audio or visual threat like a light or the player, but we have reached the target. Remember, just because we've reached the target doesn't mean that the thing that caused that threat to be created is there anymore. Think of the player, for example. We can reach the target and it can be a visual player target, but the player might not be a visual threat any longer. Therefore, we're just waiting at the last place where we saw the player. And when this is the case, we just fall down into this code here. We don't seek left or right at all, and we just return from the function. So what we need to do really is we just need to add some of this random seeking left or right here at the bottom of the function. So we just need to say else If none of the above are true, in other words, it's not a waypoint and it's not an audio or visual target that we're yet to reach, then we'll just do what we normally do. We'll say the direction timer is larger than our direction time, seek in a random direction, and then reset the direction change timer. And of course, just like the waypoint case where we haven't yet aligned with our waypoint, we'll drop through to the bottom of the function where we'll remain in the alerted state. So I do believe now that that should fix our problem. So let's now turn the ambient light back down again for a final piece of mood. Hang on a minute. Turning the light down was an absolutely dumb idea. Let me turn it up again. There she is at our last known location, and she's frantically looking left and right as if to say, "What's going on here? I'm sure this is where I heard the sound come from." So, just to show you again, shine the light on her. Now she should be coming after us. Yes, she is. We'll sort of dodge around the corner, hopefully shake her off. And there she is, saying, "This is the last place I saw him." Dodging around this corner. Where's he gone? And now she looks like she's seen the food source and she's thinking, well, I don't know, I'll have some of that instead. Oh, and she saw me and she's coming. So we do have some problems at the moment. One of them I'm not quite sure I'm going to fix yet, which is that our flashlight collider will actually shine through walls at the moment. So if Jill was on the other side of a wall and our collider was sticking through that wall, well, then we're going to register as a threat, which is less than ideal, but we will cover that at another time. We can probably do some kind of line of sight test with the zombie and the flashlight for that, or some kind of swept sphere or capsule test, but that is for another day. So I did actually have some more things that I wanted to add to this lesson. I wanted to add the code that's going to deplete the zombie's satisfaction as it walks around the level, but I'm going to address those other issues in the next lesson, I think, at the very start of it, because this has gone on quite long enough. Thank you very much. Been quite a grueling lesson for me, this one. My voice is almost gone. So we'll do that in the next lesson. In the next lesson, we're actually going to do the attack state, okay? Because now we have our character controller in the scene, we actually have something that the zombie can attack, so that should be quite fun, don't you think? So thanks for listening, guys. I'll see you then. Bye bye now.